Welcome back. Do you remember that contraption? That's a cheap, if not the cheapest RC servo you can buy on eBay, and I made a review about it, card here, link in the description. And do you also remember that thing here, where I hardware debounced two rotary encoders with push buttons? With the help of a little chip and reading the stuff using an Arduino. Also, card here, link in the description. Back then I called the Eno file mysteriously laboratory shaker, and maybe you can see where this is going to, because that servo is doing kind of a shake. But there's a little problem. You see, your run-of-the-mill RC servo moves to the commanded position as fast as it can. So if at that point in time I give it the command to move to this position or to this angle alpha, it moves there as fast as possible. And if I give it here the command to move to this angle here, it moves there as fast as possible, and so on. That's not really what I want the servo to do. What I want the servo to do is to move continuously. And for that we will have to do some work in the software to constantly update the command to the servo where it should be. And if that reminds you of controlling the axis of a CNC machine, you're not that far off. Talking about continuous motion, yes, according to the red line, the servo would move continuously. However, here at the corner, it would change direction abruptly. And changing direction abruptly in a mechanical system, so it continues moves here and then abruptly changes direction, that always results in high accelerations, and high accelerations always result in high or very large forces. And if we can avoid huge forces in a mechanical system, that's always a good thing. So the ultimate goal is to have the servo move according to a sine function, avoiding these abrupt changes of direction here. So we would start out at one position and then accelerate until halfway point and then decelerate again until we stop. And then in the other direction, accelerate again until halfway point and then decelerate until we stop. And if that reminds you again of how software is controlling the motors of a CNC machine, you're absolutely right. Again, it's not a sine wave a CNC machine would implement, but it would implement at least some speed ramp up and then stay at a certain speed and then ramp the speed down of the motors. So, how do you control these servos? The answer is via a PWM signal, and I will talk about the details of that signal in a second. I just want to apologize to all those RC model people because I saw, at least in one discussion forum, some novice Arduino programmer came and said, okay, I want to send an PWM signal to my servo. And there was an outcry. This is not a PWM signal. It's a very special signal. It's a, I'm sorry, RC guys, but for an electrical engineer or an electronics engineer, this is a PWM signal, okay? Anyways, so base frequency of that signal, at least with the Arduino library, and normally I think is 50 Hertz. So you have a pulse width modulated pulse every 40 milliseconds. And the pulse width is compared to, the 20 milliseconds total duration, or 50 hertz, very narrow. It's typical between 1000 microseconds, so 1 milliseconds for full counterclockwise, and 2000 microseconds, 2 milliseconds for fully clockwise. And you might ask why? The answer is simple. So an RC remote control transmitter will multiplex several of these PWM signals into one carrier frequency, high frequency carrier frequency, which is sent to the RC model's receiver, where they will be demultiplexed into single PWM signals, one for each servo or function. Note, 50 hertz, 20 milliseconds. It doesn't make any sense to try to update the position of a servo any faster. Basically, it's impossible. This will become important later on. And of course, there is an Arduino library to create these PWM signals for servo control. Remember when I said these were typical values? Well, my servo here needs a pulse width between 540 microseconds and 2390 microseconds. So really just typical values. In addition, I don't want to rotate the servo full 180 degrees in my application. I just want to wiggle it a little bit. So from a 0 position, here exactly in line with the case, a little bit downwards, so it's just or not quite touching here when you have it on a surface, to an upward position, which is the mirror of the downwards position. And now I will find out what pulse width I need to get to the center and down and up, and then we talk again. So I experimented a little, and the middle position I want is at 1420. And we will have a look at that code later on. And the maximum downward position I can reach is at 1240. And then I can just slide a piece of paper through here. So it's almost touching. And the most upward position, this is, awkward, not upward. So here this would be symmetrically 1420 minus 1240 is minus 180. So 1420, our middle position, 1420 again, plus 180 is 1600. So that would be the most upward position. And sorry, that's the cable going before the lens. And that's the range of movement I want to cover with a sinusoidal movement, rotation here. Wiggle up, wiggle down. There's another important point I want to make here. We are at 1600s, and if I go now to 1599 and you look closely what happens with the servo, nothing. 1555. Okay, there it wiggles. But as a rule of thumb, setting less steps less than 155. Does it do something? No, not again. So as a rule of thumb, 1540, you should change the position of the servo. It's finding the lens is a little bit hard. In 10 microsecond increments, decrements, maybe 5 microsecond decrements, increments. Going any finer than that makes absolutely no sense. So that was the wiggle we did with our servo. Yeah, I measured or eyeballed the angles here. So neutral in the middle, 0 degrees. And when we were completely down, minus 15 degrees, completely up, I call that plus 15 degrees. And yeah, so we cover here a 30-degree angle. And our PWM signal, yeah, the pulse width is between 1240 for down position, 1600 up, and in the middle 1420. So a total difference of 360 microseconds. Next, I want to know what's the fastest speed my servo has to be going, yeah, in degrees per second for certain wiggle frequency. Remember, we want to have a sinusoidal movement, so our servo speed is basically almost 0 at these points and reaches the maximum here in the middle. And for that we will have to do some math. I'm really sorry, trigonometry. But if you really want to do some, motion movement, here with an RC servo, but also for a CNC machine, maybe you want to program your own Gerbil, you will need to do some math. Sorry. So, the blue line here is our sine wave as we know and love it from the oscilloscope. And ignore the red stuff for the moment. The mathematical sine function is defined as going from here on the y-axis from 1 here at the top to -1 at the bottom, and a full cycle goes from 0 to 2 pi. That's simply, or 360 degrees if you want. That's simply the definition of the sine function. And our servo, of course, reaches its highest speed, angular speed, if you want, at these points. Here, here, and here. So always when we cross the middle position. And our angular speed is equivalent to the steepness of the sine function at these 3 points, which is 1 and 1 and -1, or if you put a tangent through these points, 45 degree lines, -45 degree, 45 degree, 45 degree line. Mathematically speaking, the steepness of the sine function at any point is its derivative. And incidentally, the derivative of the sine function is the cosine function, which is just again a sine function, but just shifted -90 degrees or -pi/2. So this would be the cosine of that sine. And as you can see, it's here +1 and here it's -1. And yes, I used that thing here to draw these nice sine waves. Now, let's finally calculate our angular speed here at the middle. And now we go to the red stuff here. So 1 and -1 obviously is -15 degrees and 15 degrees. And a full sine wave, 2 pi, is 1 full cycle. So 1 cycle as in cycle per seconds or in hertz. And we know the steepness here is 45 or -45 degrees or 1. So we have to look at the points of pi +1 and pi -1. Yeah, this gives us this nice -45 degree line here. And we have to scale that down to 1 of this axis, so to 1 cycle. So simply divide the pi values here by 2 pi, and that yields us here, these tickers would be at 0.341 and 0.659, and yeah, the distance here is 0.159. And when we take, just here one of these points or triangles, so we have 15 degrees, divided by 0.159 of our whole cycle, that gives us basically an angular speed here of 94.3 degrees per hertz. So if we exactly do that with 1 hertz once per second, we reach the maximum angular velocity here with the servo at that point of 94.3 hertz. If we do that with 2 hertz, double that. And from the review, I already carded it and linked it in the description of our servo, we know that at 4.8 volts with no loads, it moves in 0.28 seconds 60 degrees. So a total of 214 degrees per second. So with no load, we could wiggle that with a frequency of, a little over 2 hertz. But that's with no load. But keep that in mind as, our absolute maximum wiggle frequency we could reach. But what does that all mean for our software? So again, please ignore the green and the red stuff, and we just have a look at our sine wave, so the motion our servo should be doing, and the timings we need, between 1240 and 1600 microseconds, zero position B at 1420 microseconds. And if we really want to do a 2 hertz wiggle here, we have 500 milliseconds to complete, that cycle. Now, do you remember for 50 hertz PWM signal, the fastest update frequency we can have is an update every 20 milliseconds. So in total, if we go here, how many updates we can send here, that's 25 per cycle, or 25 in 500 milliseconds. Now, just as a sanity check, let's do the same thing we did with the sine wave. And now the red stuff comes in. We don't want to know how big our biggest update is. You remember I said, between 5 and 10 microseconds, that's where you can actually see a movement. If our update or single update would be a little bit bigger, we would get kind of a jerky motion, something like that. But looking at our middle point again here and scaling the whole thing to 1 again, 20 milliseconds, that is, in a scale from 0 to 1, we go from 0.5 to 0.54, that's 0.04. So a single 20 millisecond ticks. And I haven't drawn in to scale all the 25 ticks here. Scaling our PWM microsecond scale here to -1 to 1, we get here 180 microsecond is 1. So 180 microseconds time 0.04. What we get here, our greatest update, that's a change of the PWM signal of 7.2 microseconds. And that's exactly in the ballpark between 5 and 10 microseconds we talked about that we want to achieve. So this should work up to a frequency of 500 milliseconds or 2 hertz, 2 wiggles per second. I should mention at that point that this is only one strategy to do motion control. We have fixed ticks in time and we calculate our servo signal for each tick. If you have a CNC machine with stepper motors, you would do it exactly the other way around. you would calculate the time steps when you have to actually to advance your stepper motor exactly one step. And that's how that wiggly sinusoidal motion looks like at 2 Hertz. It's actually probably a little bit faster than 2 Hertz. Yeah, we have a look at the code in a second, but you also noticed I switched over to my Arduino Nano Every that I used in that other project I mentioned in the beginning. Yeah, there was a card, link in the description, with the 2 rotary encoders. I wonder why. Anyway, let's have a closer look at that wiggle. It certainly looks smooth, but is it really sinusoidal? So most of the code I have here is from the hardware debouncing rotary encoders video. I already carded it, link in the description. And I'm not using any of that currently. However, I added some code to make our servo wiggle, and we will go over that right now. So of course I need the Arduino servo library. And I need a constant for our servo pin. It's a PWM pin, of course, number 9. And then I have 4 variables here. So first our servo 0, that's the middle position in the PWM pulse width in microseconds. That's 1420. And then the maximum servo stroke we want. That's basically the 1420 plus minus 180 microseconds, to get into the upper and the lower position. Then I have here something called quadrant steps. Remember, we are using trigonometric functions, so circular function. And a circle has 1, 2, 3, 4 quadrants. And in each quadrant, I go through 8 steps, with my PWM pulse width. And you remember we calculated we can have at most at a 2 Hertz wiggle 25 steps. And probably you noticed 4 times 8, so the 4 quadrants times the 8 steps I do in each quadrant, that's only 24. And therefore we are 4% faster than 20 Hertz because I stayed with my step duration at the sensible minimum for 50 Hertz PWM signal of 20 milliseconds between each step. And of course I have a servo object here. And that servo object is, of course, initialized. So I attach that servo pin, pin number 9. Has to be a PWM pin, I think. And I initially, to get it into a defined position, write to it, the PWM pulse width of servo 0 plus servo stroke. So we move the servo, or tell the servo to move into the top position, and then I just wait 1 second. And now comes the loop that's a little bit more complicated. In the loop, I have 2 variables which are important. That is a quadrant, that's the current quadrant of the circle for our circular trigonometric function. The current step we are inside that current quadrant, and these variables at the moment don't have to be initialized, nor do they have to be static, but we need them. Ignore the rest here for the moment, and we come here to that loop. And that loop loops, of course, through the quadrant, but we are in C++, so they are not numbered 1, 2, 3, 4, but 0, 1, 2, 3. And we loop through our steps inside the quadrant, and yeah, from not from 1 to 8, but from 0 to 7. And then I write a signal to the servo, and that's the servo 0 position plus the servo stroke, yeah, our maximum stroke, times, and here we don't have the sine but the cosine. I explain that later. But the cosine is also basically defined, yeah, or its output is between 1 and -1. So we get at most servo stroke plus servo stroke times 1. So full upwards, or servo stroke plus servo stroke times -1, so fully downward. And here we start with half pi. Remember that sine or cosine function, they are defined between 0 and 2 pi. So 1 quadrant is, yeah, just covering half pi. I divided that through the steps in the quadrant, and then I multiply that by the current step we are in the quadrant plus quadrant more times quadrant steps. I mean, it's self-explanatory. If you would put that into one loop, this would basically just count up, this term here would just count up from 0 to 23. And then, yeah, we delay for our step duration in milliseconds. Yeah, it's math. I'm sorry, but we have to go through that. To give you an explanation why I made that code more complicated than necessary, so yeah, with the 4 quadrant stuff and using the cosine instead of the sine. And just, yeah, as a little visual aid, the 1, 2, 3, 4 quadrants I talked about in the video of the circle. Let's start with the cosine thing. You remember I initialized the servo to the top position here. And the sine wave would start here at 0. So right out of the bat, I would have a big jerk down here. And I want to avoid large accelerations and, yeah, large forces. So instead I take the cosine function, which starts at 1. Yeah, and I already mentioned it, cosine function is just a sine function that is shifted here to the left by 90 degrees or half pi. So yeah, this is just me being lazy because I don't want to subtract half pi from somewhere in my loop all the time. Then why the quadrants? Now, we probably won't do that in this video, but in part 2, I also want to start and stop that motion via the Arduino. And where do you start and stop that motion? At which points here? And I'm going back to the sine wave. That's easier here because there's a line. Well, you could do that either here at that point, because there our speed is almost 0, or yeah, mathematically at one point it is 0, or at that point. And you already guessed, because I initialized the servo, yeah, here at the very top, I will start and stop the motion always here at the very top. And, sorry, in the cosine function, that's always at the start of the first quadrant. Well, if I had one continuous loop, that would be still at the very start of the loop. But I also want to change the frequency of our wiggle. And where can we do that? Well, we can do that here when the speed is almost 0, again, or here. So basically, sorry, we go back to the cosine function. So either at the very start of the first quadrant or the very start of the third quadrant. And it doesn't stop here. I also want to be able, remember I have two rotary encoders on that board. I also want to be able to change the amplitude of the wiggle. And where can we do that? Well, obviously not at those points, because if we decrease amplitude here significantly, we have here again a jerky motion with large accelerations and those large forces, which I don't want. So instead, changing the amplitude will happen. I take the cosine, so we're at the same page. A changing of the amplitude will happen at the start of the second quadrant, when we're here at the 0 point, independent from the amplitude, we always go through the 0 point, or at the end of the start of the fourth quadrant. So when we go through 0. That's the idea. However, that loopy stuff we just did is not really suitable for that. It contains the hallmark of learn to program an Arduino in 5 minutes tutorial, a delay. Okay, and it's not what we want. So let me show you an alternative code that does exactly the same. Again, we have our quadrant and step variable here, but this time it is important that they are static, so they keep their value each time we enter the loop, and they are initialized with 0. Then I have here an unsigned long next step that's initialized with our current time, millis. That's basically a variable I will compare the millis function to see when I have to do the next step. And then I have a little temporary variable here, current time, where I store the return value of the millis function. And so now, instead of that loop, we do each time, instead of this for loop, we do each time we enter the loop the following. So I store my current time here in this temporary variable. That's just because, from line to line, millis might jump 1 millisecond forward. I don't want that. Then I compare here the current time with the time I have to take the next step. Remember, that was already initialized initially with next step. I calculate immediately the time when I have to take the next step after that. Then comes the same servo write microseconds statement as before. So we really just doing a little bit different coding for the loop. I increment my step +1, and if my step is equal or greater than quadrant steps, so 8, I reset my steps to 0 and increment my quadrant +1. And if my quadrant variable is equal or greater than 4, then I reset my quadrant variable. So this code does exactly the same, in effect, as that code here, but for each for loop we are executing here at the center, we are executing a whole loop in the Arduino code. And that, of course, gives us the freedom to do in the 20 milliseconds whatever we have between the steps, whatever we want. For example, you might remember all this encoder stuff, and we have now here exact points in the code. We know exactly in which quadrant we are, and if something happens at the encoders, we can change, for example, our stroke parameter, or we can change our quadrant steps and make more quadrants, and so have a lower frequency of the wiggle. But that's something for part 2. The servo is already wiggled by the new version of the code, and you see it does exactly the same, which was the idea. Anyway, I put a link to the current version of the code into the description if you want to have a closer look at it. And next time, as I said, we will use rotary encoders to change the frequency and the amplitude of the wiggle, and use a push button function on the encoders to stop and start the motion in a controlled manner. Till then, bye.